Hey everyone, and welcome. Have you ever just stopped and wondered why we have so many programming languages? You've got Python, C++, Java, Rust, the list goes on and on. Why isn't there just one perfect language for everything? Well, today we're going to crack the code on programming languages themselves. We're going to look at what they are, how they're designed, and why having so many actually makes a lot of sense. All right, let's get into it.
So yeah, this is really the question that kicks everything off. I mean, if the goal is just to tell a computer what to do, why all this incredible variety? And the answer, as you're about to see, is that a programming language is so much more than just a list of commands. It's a tool for sure, but it's also a philosophy. It's a whole series of trade-offs, all baked into one.
So here's our game plan. First, we're going to talk about why languages matter in the first place. Then we'll look at the design compass that guides how they're made. After that, we'll explore 4 totally different ways of thinking about code. Then we get into the nuts and bolts of how your code actually talks to the computer. And finally, we'll see how these languages handle the messy real world. Okay, first stop, why do languages matter? Before we get into all the technical details, we really have to get a handle on the why. Why do people spend years of their lives creating, arguing about, and learning all these different ways of talking to a machine? Studying programming languages isn't just some academic thing you do in school. It makes you a fundamentally better programmer, period. When you understand the core ideas behind them, you literally expand your problem-solving toolkit. You start to see problems from different angles. It means you can choose the right language for a job, not just the one you're comfortable with. And maybe the best part, it makes learning the next new language so much easier. And this slide just perfectly illustrates the whole reason we have so many languages. Think of them like tools in a toolbox. You wouldn't use a sledgehammer to put in a tiny screw, right? Well, it's the same idea here. For heavy-duty scientific math, you got Fortran. For old-school business reports, there was COBOL. Artificial intelligence needed a way to work with symbols, not just numbers. And that gave us Lisp. And for building efficient operating systems, C was the king. Each area has its own unique challenges, and that's why we have specialized tools for each one. All right, moving on to our second section. You see, languages aren't just accidents. They are carefully engineered. And that whole engineering process is guided by this set of criteria, kind of like a design compass. And it's all about making tough choices and trade-offs. And this right here is one of the classic battles in language design, readability versus writability. On one hand, you want your code to be super easy for another human to read and understand. That's readability. But on the other hand, you might want a language that lets you write really powerful stuff, really fast, in just a few lines. That's writability. For instance, a language called APL lets you do insane amounts of work in a single line of code. Amazing writability. The problem? For anyone else trying to read that line, it can look like complete gibberish. So you see the trade-off? You often have to sacrifice one for the other. And that's not the only balancing act. Language designers are constantly juggling other huge factors, like how reliable is it? Does it have features that help you catch bugs before they cause a disaster? What's the total cost? Not just to write the code, but to train people, to run it, to maintain it for years? And how portable is it? Can you write it once and run it anywhere? These are the big questions that really define what a language becomes. Okay, now for one of my absolute favorite topics, paradigms. A programming paradigm is way more than just a feature. It's like a whole philosophy. It's a completely different way of looking at a problem and structuring your solution. This chart gives us a fantastic bird's eye view. First, you've got the imperative paradigm, like in C. This is the classic step-by-step recipe. Do this, then do that. Then there's functional, like Lisp, where everything is treated like a pure math function. The goal is to avoid changing data if you can. It's a totally different mindset. Then you have logic programming with Prolog, which is wild. You basically just state a bunch of facts and rules, and the language figures out the answer for you. And finally, object-oriented, which is everywhere today in languages like Java and C++. It's all about bundling your data and the code that works on that data together into neat little packages called objects. So, we've talked about the why behind different languages and the big ideas that shape them. But how does the code we actually type on our keyboards turn into something a real computer can understand and run? Let's follow that journey from idea to execution. So it really all starts here, with the basic blueprint for almost every computer made today, the von Neumann architecture. The core idea is simple. You have a central processing unit, or CPU, and it pulls both its instructions and the data it needs from the same shared pool of memory. This constant fetch an instruction, execute it, fetch the next one cycle is literally the heartbeat of your computer. And it's the very reason that imperative languages, those step-by-step recipes we talked about, feel so natural. Our code often directly mirrors how the hardware underneath actually works. Okay, so you've written your code. Now you have two main ways to get the machine to run it. The first is compilation. A special program called a compiler reads your entire program and translates it all at once into super fast machine code. The translation part can take a little time, but the program that it spits out is incredibly fast. The other way is interpretation. Here, an interpreter reads your code one line at a time and executes it right then and there. There's no separate translation step, which is great for development, but the trade-off is that it runs way, way slower. Think of a compiler as a sophisticated assembly line for your code. First, the lexical analyzer breaks your code into little meaningful pieces called tokens, things like keywords, numbers, and variable names. Then the syntax analyzer checks to make sure your code's grammar is correct, kind of like a spell checker for code. After that, the semantic analyzer checks if it all actually makes sense. And finally, after all those checks, the code generator builds the actual machine code, which then often gets optimized to run even faster. It's this whole multi-step process that turns your human thoughts into pure machine instructions. All right, let's wrap this up by touching on a couple of advanced but totally critical concepts that modern programming languages have to grapple with to build the kind of powerful software we all rely on every single day. Concurrency. This one is absolutely essential in the modern world. Just think about your web browser right now. It might be playing a video, downloading a file in the background, and still letting you scroll smoothly. It's doing all of that at the same time. Well, that's concurrency. It's the art of having a program juggle multiple tasks at once. It's incredibly complex to get right, and giving programmers good tools to handle concurrency is one of the most important jobs of any modern language. So what happens when things go wrong? Like, what if your program tries to open a file that just isn't there? Without something called exception handling, your program would most likely just crash and burn. Exception handling is basically a safety net. It gives you a structured way to try doing something risky, and if an error happens, you can catch it and decide what to do next instead of just letting the whole application die. It's what makes software robust and reliable instead of fragile. So there you have it. We've seen that languages are specialized tools, that they're shaped by all these design trade-offs and different ways of thinking, and even by the hardware they run on. They're always changing, always evolving, which leads us to one last big question. With AI getting better and better at writing code for us, what does that even mean for the future of programming languages? Will our languages get simpler, more abstract, or will they become something else entirely? That's a question for the next generation of coders and creators to answer. Thanks so much for tuning in.